Mega Mechatronics.
Welcome back to Mega Mechatronics. Today we're going to be talking about shot peening. We're going to be looking at the optimization of that process and controlling this. And this will be for like critical applications. So you're going to find a lot of good information, some good tips to help you figure out what you need to do with your process to make it better and make it optimized to perform the best. And remember, shot peening is not shot blasting. We are not, this is not a cleaning or an abrasive process. We are using high specification material to impart residual stresses into the parts, and that's what we're going to look at. Compressive residual stresses. So we're going to produce these stresses by transferring kinetic energy from a moving mass. So imagine you have a ball peen hammer, and you're hammering on a surface on a piece of steel. And that's going to leave little dents. So under those little dents are going to be some compressive residual stresses. So that's what we're doing with very small diameter spheres of metal or even ceramic. So we're going to transfer this kinetic energy into the surface in addition to coverage density. So coverage density, imagine you are spray painting or painting a wall. You need to make sure you cover every single portion of that wall with that whatever color you are painting it with. If you miss a spot, that spot's not going to be painted. If you're spray painting a poster board, imagine that paint coming out of the can is little balls of steel, and you're spraying some metal. You need to make sure you cover every single portion of the metal that needs to be shot peened, that needs the fatigue life increase, because that's what we're doing with these residual stresses. We are improving the fatigue performance of certain systems. And of course, the formula for kinetic energy is 1/2 times mass times the velocity squared. So the transfer of kinetic energy. And we're looking at the mechanics involved with the properties of the shot. So shot hardness, that shape of the shape and structure, as well as the properties of the workpiece. So in a little diagram here up top, we see that little red line showing the path of that sphere at an angle, and it creates that dimple. So if we look below that, we have our stretched surface and the compressive residual stresses that have been imparted into the surface. So factors controlling kinetic energy with shot peening or shot blasting, shot peening process is not shot blasting, is the shot velocity. So again, 1/2 mass times velocity squared. This is the velocity portion. So that could be the speed of the wheel with the wheel systems, or air pressure with the air and nozzle and the nozzle size. So you can imagine a smaller nozzle will be accelerating the shot at a faster speed, faster velocity than a larger nozzle. The impact angle. So a good analogy for this is like tank armor. So the really early tanks had flat vertical walls in the tanks. So the projectiles being shot at them will impact the surface perpendicular to that piece of armor that's going up and down. And so all of the energy in the projectile is being transferred to that steel armor plate. So what happens? Well, the projectile goes into the tank and kills the tank crew. So what they figured out is you can actually angle the surface to help deflect that, in addition to in increasing the thickness that the projectile sees, because the armor's on an angle, so the area, the horizontal area is actually larger, or the horizontal thickness. However, we're deflecting the projectiles. That's another benefit, is you're because it's much stronger. So that kinetic energy is only a portion of the kinetic energy is being transferred into the tank, and the rest of it is dissipated by the projectile flying wherever it's flying. And it just keeps on going, and the tank crew is safe. So the shot mass, the shot chemistry, and again, going back to the war analogies, so the bigger the bullet, it's going to hit a lot harder. And if that bullet is a lead core versus a steel core, it's going to do way more damage. The steel core is going to do way more damage, or even a tungsten core, as well as the workpiece properties. So how much residual stress can that workpiece actually create? So how can we monitor the kinetic energy? Well, we're going to use almond strips. And what an almond strip is a standardized, a small standardized piece of metal. It's only a handful of millimeters in size. I can't remember the size off the top of my head, but you could Google that stuff, almond strip. So there's different strip standards. We have the N strip, A strip, and C strip. So the only difference there is the thickness of that strip. So in our little model here, we have our blast nozzle shooting the shot at the surface, and the almond strip is actually attached to a very hardened block, the holding fixture. So what this allows is for the shot only to hit the one side of the surface, and because it imparts a certain amount of residual stress, when you pull it out of that fixture, that strip is actually going to arc up, and you see there's an arc height there. So the more you shot, the more residual stress, the more that's going to arc in a certain range, depending on the strip that you're using. So if your process is really, really, really strong, you're probably going to use like a C strip. If you're using smaller shot and on maybe smaller parts or something, you'll use the N strip. And then these arc heights are measured in a standardized test fixture. So it's just a precision gauge with a precision dial indicator, and you have your flat check block. You stick it on there, clean off all that shot crap. And then you zero it out, and then you put your strip on there, and you can measure and record the amount of arc height. So this is just a proxy for that kinetic energy in measuring it. So if everyone, all the engineers and everyone in your country are using almond strips, then it's like a universal language. In addition to that, you can do residual stress measurements with X-ray diffraction, where you're shooting X-rays and looking at the crystal structure and gauging the residual stresses. In addition to mounting the part and polishing it, so the side profile, and using a precision hardness tester, you measure at certain depths from the edge of the surface of the part. So the more residual stress, the higher hardness it's going to be. And here's a plot at different depths of that residual stress. And we sort of touched on this in the failure analysis video. And I think so. The blue is the baseline that looks like as peened, and then they did some tempering processes, it looks like, and it sort of removed the residual stresses on the surface there. So now we're going to jump into coverage and coverage density. Remember that spray paint analogy? So what are the factors affecting the coverage density? So the density would be like how much paint is built up in certain areas of whatever you're painting, using that analogy. So that's the number of impacts affects the coverage density. So that's related to like shot flow. The exposure time. How long has it been in the tumbler, or how long, or how fast is that conveyor belt moving if it's that type of process? And density is also affected by the shot properties, the size of the shot and the chemistry makeup, like the hardness of that shot, and whether it's ceramic or cast. And workpiece properties. So is how hard is it? It's going to take longer to get a good coverage on a harder material, workpiece. How do we monitor coverage? How do we gauge that? Well, we visually inspect it. So you can either run your workpiece or run a lot of them through a lot, a subset of them through at different times as you're developing your or optimizing your process. So you send them through, you pull them out, you take it to a microscope, and you start looking at the dimpled areas, and then looking for areas with no dimples. So if you're not 100% covered, there are going to be some as raw surfaces in there that have never been touched by any shot peen. And coverage exceeding past 100%, you really can't determine it accurately. And it all depends on the material. There are some dyes out there, some fluorescent dyes. You can coat the parts that are, pretty hard, and then send that through, and then you look at it under a black light and look for any of that residual stuff. But that stuff, it's not really the best gauge or the most optimized method, because a piece of shot could hit the workpiece at a low angle and deflect and not really impart residual stresses. However, it may be enough to scrape off that coating. So it could give you some false positives there. So the number of impacts, so the number of times the shot impacts, a single piece of shot impacts your workpiece, is actually linearly proportional to the flow of your process and the exposure time within there. However, the coverage is not proportional, and we'll see why. So when 100% coverage is achieved, we're going to call that 1T, an exposure time of 1T, or 100%. So specific locations have been impacted multiple times, just because the process is completely random under that blast stream, assuming everything with your equipment is properly calibrated and set up correctly. We'll just call that completely random. So at 1.5T, 150% coverage, 5 or more impacts have occurred at 52% of the locations. So half of the part, 52% of the workpiece, was impacted 5 or more times. So let's say the one half of the part has only been hit 1 time. The other half, we know, has been hit 5 or more times. And at 2T, 200% coverage, so that's twice the time it takes to reach 100% coverage. 5 or more of locations, 5 or more impacts have occurred at 84% of the locations. So we haven't, even though it went through at twice the time, just because it's random, only 84% of it have been impacted 5 or more times. So how does the media, how does that shot peen, that raw, the spheres of ceramic or steel, That's what we're talking about when we say media. So the size of the shot, smaller shot actually produces more impacts per pound, therefore achieving the coverage much faster. As well as the chemistry and the hardness. So just a generalized way to think of it, a hard shot or a hard media impacting a soft workpiece is going to cover much faster than the opposite. If you have a softer shot that is impacting a harder workpiece, it's going to take longer. Now we're going to get into the optimization of the process, and we're going to be looking at the fatigue life and the amount of residual stress that you are imparting into the surface. So here's a test we have, and this really does depend on the material, so we're only going to look at a few examples here. And with your application, you're going to have to find ways to optimize that, but what we're looking at are the ideas behind and the concepts behind this optimization process, and actually how you deteriorate or diminish the fatigue life with increasing the coverage. So as the factor of media stream energy increases, the fatigue life will rapidly increase. So starting with a raw part workpiece, and you send it in there, the fatigue life is going to increase with that amount of time that it's in the process. And then it peaks, and then it almost diminishes in fatigue strength as fast as you gain that fatigue strength. And what media stream energy is, it's related to the coverage at a flow rate. And again, this is sort of a universal language to compare processes. The media stream energy. So think of that as the coverage amount. So the more media stream energy, the more coverage. So again, looking into the effect of fatigue life. On this graph here on the vertical axis, we see the time to crack. So the fatigue life until the part cracks in the amount of hours compared to the peening intensity, which is actually the almond strip heights. I'm going to have to grab a drink of water here while you check out these graphs. So you see that peak we're talking about as the peening intensity goes up, or which is the same media stream energy goes up. You're going to see that peak off and then rapidly diminish. And then the graph on the right, same concept. So we have our fatigue strength scale versus that media stream energy. So you see it really quickly peaks and then it really drops off. It's not like we're damaging the raw material strength, but we're not optimizing. We're not maximizing that fatigue potential, that fatigue strength increase potential. So even tests on aluminum show diminishing fatigue life with that excessive coverage, that excessive media stream energy. And just, repeating that with increase in intensity. So we're turning up that blast wheel, we're turning up the air pressure. That's not really doing good. And now we'll look at how this coverage affects the residual stress. So looking at that 1074 again, we see that sharp increase in the residual stress with that increasing media stream energy. But once that peak is reached, there's no benefit to continue processing that part. But on a different material, you can imagine, hopefully you're not using this material, it actually shows a reduction of residual stress, which is going to be related to your fatigue strength. So the more residual stress, the likely better fatigue life you are going to achieve. So those are interrelated. So you could see on this graph here, again, the residual stress on the vertical axis, and up top we have our horizontal, that's the time, the peening time, which is related to coverage, and that's related to media stream energy. And you see the lower those lines are, the more compressive residual stresses you have, and or the max. This is showing the maximum, and you see how it does increase that residual stress to a certain point, and then it starts dropping off again. So you are potentially losing fatigue strength if you keep it in there for too long, or it's not in there for long enough. So again, we're looking at more developmental examples, or more, just more examples of why you need to optimize this system and do some testing. You are going to have to do some fatigue testing at different parameters. So we're testing 4340 again, and what it showed maximum, the fatigue strength was realized. That maximum peak fatigue life was realized at 80% coverage, or I believe that's it's supposed to be 0.8 T. So at 80% coverage, it reaches its max fatigue strength. So from 80 to 400% coverage, it showed that the residual stress profile remained unchanged, and it didn't show any benefit to the depth of the residual stress and coverage. And again, with another test, the 4-point bending test of the same material, it showed a decrease in fatigue strength with 300% coverage when compared to an 80% coverage. So you can see how leaving it in there longer is actually worse than not even getting full coverage. So some additional notes. The surface finish does play a factor in the fatigue life of the part. And this, in my experience, I did high performance springs, and we found that polishing the springs prior to the last step of the shot peening process performed much better than not polishing the part and then shot peening it. So we polish it to the thing shiny, it's like a chrome spring, and then we shot blast that, and it actually performs better. So it's necessary to establish these optimum peening conditions through the examples, through testing, like we talked about. And something to consider is the shot will actually deteriorate. The shot doesn't last forever. Ceramic shot, that stuff's going to fracture really easily. Same with cast shot. That stuff's going to fracture and break down. Condition cut wire is pretty good, pretty tough, durable stuff. It's not really going to fracture. It's just going to wear down to a smaller size. And the blasting system. So the nozzles are going to wear out. And that's going to change your flow. And that's going to change your velocities. And the blast wheels wearing out. The paddles are going to get smaller, and the tip speeds are going to be off. Not to mention vibrating like crazy. So you need to create accurate specifications for that intensity, those almond strip measurements, those residual stress parameters, as well as coverage. So that's going to be the time. Time is very important. As well as specifying the correct shot and ensuring the correct shot gets put in the machine. Otherwise, you're going to lose all those benefits. It still might increase the fatigue strength, but you're going to lose your safety factors. Or you're totally going to negate them if someone puts the wrong shot in the machine. And I would say the ultimate challenge after you figure out your process is maintaining the intensity and the media stream energy. That's going to be, you're going to have to be careful with the type of equipment you choose and the maintenance of that equipment to make sure you sustain your goals. And that'll do it for our shot peening video here. And I'd like to thank the Shot Peening and Blast Cleaning Workshop the 18th annual one in particular. That's the one I attended. Well, if you guys liked this video, if you found it interesting, please don't forget to hit the like button. It doesn't, I'm not getting anything. I am getting soft benefits out of it because it shows that I did okay, and I should make more videos like this. And if you guys do want to see more videos, don't forget to subscribe. Thank you so much for watching, and have a great day.